So when you're dealing with this kind of notation, there are three Greek letters that you'll consistently see. They are omega, theta, and omicron. Omicron is better known as O, as in big O. And big O is the one, of course, that you're going to see most often. So to explain this, I'm just going to bring up an array. Let's say we're going to build a for loop to iterate through this array until we find a particular number. If we're looking for the number 1, this is our best case with the least number of iterations through the array. This would be our worst case. And 4 would be our average case. So this best case is represented with the Greek letter omega. This average case is represented with the Greek letter theta, and our worst case is represented with omicron or O. So big O is always going to be worst case. And I want to point this out because it is very common for people to say things like, okay, that's your worst case big O, but what's your best case or average case big O? Well, technically there is no best case or average case big O. That would be omega or theta. So when we measure big O, we are always measuring worst case. So our next big O notation is O of 1. So let's start out with some code here. We have a function called add items, and all we're going to do is we're going to return in plus in. There's only one operation here, and that's the addition. So it doesn't matter if in is 1 or in is a million, the number of operations is going to be 1, and that is O of 1. Well, what if we add another addition? Well, now that's 2 operations, right? O of 2. And as you may have guessed, we're going to simplify this and make it O of 1. So O of 1 a lot of times is referred to as constant time. So this situation here where we have 2 additions, it's 2 operations. That is constant, no matter what in is. The number of operations does not change as in changes. So let's take a look at this on the graph. It's just a flat line across the bottom. It is the most efficient big O. Nothing is more efficient than O of 1. Remember, you will also hear this referred to as constant time. So if you hear that phrase, that is O of 1. So after this video, we're going to have our first quiz. And I want to talk a little bit about that because it's going to be one of the 2 ways you'll be able to apply what you're learning in the course. But the quizzes will be where you spend maybe 10% of your time applying what you're learning. The other 90% is going to be coding the data structures and algorithms that we're learning in the course. So there are 2 big things you want to get out of a data structure and algorithms course. First, obviously, you want to be able to code all of these things. But the other thing, when you walk into a job interview, is they will ask you questions about what data structure, what algorithm would you use in a particular situation. All those questions at the end of the day are based on one thing, and it is big O. So the quizzes are going to focus on big O. That's going to be the best way to test how much you know about big O is with a quiz. The best way to apply your learning with coding is to code. So I won't have any coding questions in the quizzes. The quizzes will be solely based on big O. The coding will be done when you pause the videos, when we're in the middle of learning a data structure, and you go write the code and come back and see if your code was correct. That's the best way to learn to code, is to code. So with that, let's get into the first quiz. It is essential that you understand big O when you go into a technical interview, because this will absolutely come up. Understanding this will also make you a better coder. So what is it? So think of it like this. We have 2 sets of code. We have code 1 and we have code 2. How do we determine which one is better? Now, both of these are going to accomplish the same thing, but they're written differently. Is code 1 better? Maybe it is easier to read. Or is code 2 better? Well, maybe there are other things about that make code 2 better. Well, Big O is a way to mathematically figure out which of these two is better, which one runs more efficiently. So obviously we can't measure this with a scale, so I'm going to bring in a stopwatch to make the point. Let's say we run code 1, and when we run it, we start a stopwatch, and it runs for 15 seconds. Then we reset the stopwatch, and we run code 2, and code 2 runs a lot longer than 15 seconds. Well, obviously we want our code to run as quickly as possible, be as efficient as possible. So by this measure, code 1 is the better code. This is what is called time complexity. But we don't measure time complexity in time. We measure it in the number of operations. And the reason we do that is if you took the same code and we ran it on a faster computer, obviously it would complete in less time, but the number of operations would be the same. So either way, on the fast computer or the slow computer, the time complexity would be the same. The number of operations would be the same. Also with Big O, we measure what is called space complexity. And space complexity is the amount of memory that something uses. So let's say code 1, while it's very fast and runs in 15 seconds, or comparatively fast, maybe it uses a lot of memory. And then we reset all of this and we look at code 2, and while that runs a really long time, the full minute, maybe it uses less memory. And if this is what's most important to you, maybe code 2 is better now. We are going to look mostly at time complexity, but space complexity will come up in interviews. They'll ask you, okay, you wrote this code in such a way, maybe during a whiteboard session or something like that. And they say, great, you've optimized for time complexity, but what if we care about space complexity more? How would you write it then? You will have to understand both concepts. But what we will focus on mostly in this course will be time complexity. So now we're going to look at our first Big O notation. And I start with O of n, not because it's the most efficient or least efficient, but because I think it's the one that's easiest to get your head around. So I'm going to explain this with a function. And I'm going to call this function log items, and we're just going to console log out some items. So we're going to run a for loop, and the for loop is going to run n times. And then we're going to console log out I from the for loop. And that's it. Pretty simple code. So let's go look at this in Chrome DevTools. So there is our function. We're calling it with the number 10. And let's run this. And you can see that we've console logged out 0 through 9. So let's go back over to our other screen. So this is an O of n operation. So to put it another way, we pass the function the number n, and this ran n times. So we passed it a 10, and it ran 10 times. It output 10 things. That's what O of n is. So let's take a look at this on a graph. O of n is always going to be a straight line. It is proportional. The number of operations is going to be proportional to whatever n is. So on this graph, this axis represents n. This axis represents the number of operations. Okay, so that is our first Big O notation, and we'll be adding to this graph with the other Big O notation so we can compare one against another. But for now, that is O of n. Big O has several ways in which we simplify the notation, and it makes things easier. The first that we're going to look at is called drop constants, or you'll see it referred to as remove constants. You'll see it both ways. So to explain this, I'm going to start by bringing up the code that we had in the last video on O of n. But I'm going to add a second for loop that's identical to the one above, except that we're going to use j instead of I. And both of these for loops are going to run n times. So let's take a look at this in DevTools. There's our code, and we're going to call this with a number 3. Okay, so let's run this. And our output is 0, 1, 2 from the first for loop, and then once again 0, 1, 2 from the second for loop. So let's go back over here. So our code ran n plus n times, or 2n. So it would make sense to say that this is an O of 2n operation. But this is where that simplification comes in. It doesn't matter if it's 2n, 3n, or 100n. If there's a constant, we drop the constant, and we say that this code is O of n. So our first rule for simplifying our big O notation, drop constants. So now we're going to look at our next big O notation, which is O of n squared. So we're going to start this off with the code that we used in the last video, where we had a for loop followed by another for loop. But I'm going to change this, and we're going to remove the console logs, and we're going to nest one for loop inside of the other. And then our console log is going to be for I and j inside of the two for loops. So let's go over to DevTools. And there's our code, and we're going to call this with the number 10. So let's run this, and if we scroll up to the top, we start with 0, 0, and if we scroll to the bottom, we go to 99. So we output 100 items. So let's go back over here. The number of items that were output, in this case, is n times n, or n squared. And that's where we get our O of n squared. Now let's take our code and add one more thing to it, because I want to point out a thing that we do for simplifying this notation. Let's take our for loops one layer deeper. Then we'll console log out the variable for that for loop. And let's take a look at this in DevTools. Okay, there's our 3 for loops. Once again, we're going to call it with the number 10. And we'll run this. So we end in 999 at the bottom there. And if we scroll all the way to the top, we have 0, 0, 0. So we had 1,000 things that were output in this case. Let's go back over here. So we had n times n times n operations, or 10 times 10 times 10, since we passed it the number 10. So this is n cubed, which would be O of n cubed. But it doesn't matter if it's into the third, into the fourth, into the 10th. We are still going to write this as O of n squared. We're going to simplify this. So let's take a look at this on a graph. So if we had two sets of code that accomplished the same task, and one was O of n squared, and the other is O of n, the O of n code is better, because it's going to complete the task in fewer operations. So this is our first opportunity to see how it is that we could compare one code set against another. And O of n squared is generally considered an efficient code. If you can write your code in a way that is going to become O of n, it is going to be much more efficient. So that is O of n squared. Drop non-dominance is another way that we simplify big O notation. So to explain this, I'll bring up some code here. This is our nested for loop that we saw from before. What I'm going to add to this is an additional for loop that comes after the nested for loop. Let's take a look at this in DevTools. So there's our code and we're going to run this with the number 10. Okay, I'm going to scroll to the top to begin with. So we have output here is 0, 0, and this goes through to 9, 9. This is our nested for loop. That second for loop that follows it goes from 0 to 9. So let's take a look at this over here. That nested for loop ran O of n squared times. The second one ran O of n times. When we add these together, this becomes O of n squared plus n. So if you think about this in terms of if n was 100, n squared would be 10,000, where the single n that's added to it in this equation is only 100 more. It's not really affecting the number of operations. N squared is the dominant term, and n by itself is the non-dominant term. So we just remove it. So we drop non-dominance. So the last big O that we're going to look at is O of log n. So I'm going to explain this with a sorted array. And in order to do what I'm about to do here, you have to have sorted data. Let's say you want to find a number in this array. And we're going to look for the number 1. What would be the most efficient way to find that? What we're going to do here is we're going to take the array, we're going to cut it in half, and say, is the number 1 in the first half or the second half? Well, it's not in the second half, so we don't even have to look at any of those numbers. And that may not seem like a big deal when you have an array with 8 items in it. But if you have an array with 1,000,000 items in it, you just made it where you have 500,000 items that you don't have to look at. So then we do this again. We cut this in half. It's not in the second half. We're going to remove that. And then we do it again. And now we have found the number 1. This is a technique called divide and conquer. So let's bring everything back here and count the number of steps that we went through to find that item. It was 1, 2, 3. And remember, we had 8 items in the array, and 2 to the third power equals 8. So I'm going to turn this into a logarithm. And if you're not a math person, don't worry. We're not going to go deep into this. But look at the 3 numbers we have here, the 2, the 3, and the 8. Log sub 2 of 8 equals 3. I'm going to back this up, and we'll look at this again. Log sub 2 of 8 equals 3. We're basically saying 2 to the what power equals 8. 2 to the what power equals 8. Well, that number is 3. To put it another way, if we take the number 8 and we repeatedly cut it in half, we divide it by 2, how many times do we have to divide it by 2 to get down to 1 item? And that is 3 times. And the real power of this is when we get to very large numbers. Let's say we have log sub 2 of this number, and this is over 1 billion. How many times would you have to cut this number in half to get down to 1 item? And that would be 31 times. To put it another way, 2 to the 31st power equals this number here that's over 1 billion. So if you had an array with 1 billion items in it, and you were going to iterate through that array linearly to find something, and say what you were looking for was the last item, you would have to look at 1 billion items to find it. But if you use divide and conquer, you could find any item in that array in 31 steps. And that is the power of O of log n. So now let's look at this on a graph. And see that this is very flat. Not as flat as O of 1, of course, but very flat, very efficient compared to O of n and O of n squared. At this point, I want to show one other thing on the graph. I'm not going to talk about this in a lot of detail, but I just want to show this. And that is O of n times log n. that is used in some sorting algorithms. And this is the most efficient that you can make a sorting algorithm unless you're sorting only numbers. But if you're going to sort multiple types of data, you're going to sort strings, this is as efficient as you can make a sorting algorithm. We will talk about this and how we came up with n times log n when we get to those sorting algorithms, because it'll make more sense then. So that's why I'm not going to talk about this now. I'm going to take this back out. So for the rest of the course, everything that we look at is going to be one of these four. So that is O of log n. Different terms for inputs is a very popular gotcha technical interview question. And to explain it, I'm going to bring up some code that we've seen before, where we have a for loop followed by another for loop. And if you'll recall, each of these ran n times, and it was O of 2n, and we dropped the constant and it became O of n. So the trick interview question is that instead of passing this in, we're going to pass it two variables. And the for loops run, the first one is going to run a times, and the second one is going to run b times. Now here is the kind of knee-jerk reaction if you don't know how to do this, is, well, this one is a for loop, and a single for loop is O of n, and this single for loop is O of n, and we're going to add these together, and that becomes O of 2n, and we're going to drop the constant, and this becomes O of n. But that is not correct, because you can't say that A is equal to n and B is equal to n. You can't have both variables be equal to n. Because what if A is 1 and B is 1,000,000? Those are very different for loops. So what you have to do is say the first for loop is O of A, or whatever the variable might be, and the second one is going to be O of B. And when you add these together, O of A plus B is as far as you can simplify this. Similarly, if these were nested for loops, this would become O of A times B. You can't use n, you actually have to use different terms for inputs. So now we're going to talk about the big O of arrays. And it's important to understand this so we can compare arrays to the other data structures that we're going to build. So I'm going to start with an array, but I'm going to present it like this. So we have the indexes there, because this will be important for explaining the big O of arrays. So we're going to start with an array that we've already created that we call myArray. And then we're going to push an item onto the end. So myArray.push is going to push this number 17 onto the end with that index of 4. The important thing here, though, is that we do not have to reindex this or this or this all the way down to the beginning. Likewise, when we remove this item with a pop, and we pop that off, we don't have to reindex anything. And because of that, push and pop are both O of 1 operations. But it's different on the other end of the array. So let's bring up myArray, and we're going to shift that first item off of the array. When we remove this, the problem we have is that this index is incorrect. The first item in the array should be 0. So this has to be reindexed to 0. And the next item has to be reindexed, and the next item. Likewise, if we do an unshift and we bring that 11 back, we have to reindex everything in the array all the way down just to be able to bring this back. Not a big deal when we have a small array like this, but if we had one that had thousands of items, that's a lot of reindexing. So this is O of n, where n is the number of items in the array. Very important with arrays to understand that on this end, adding and removing are both O of 1. On the other end, removing because of the reindexing and bringing it back because of the reindexing are both O of n. Now, let's look at adding something into the middle of this array. So we'll say my array dot splice. And if you haven't seen this before, what we're saying with this is we're going to put something in at the index of 1. This 0 means we're not going to remove any items. And this means we're going to add an item with a string that says hi. So let's open up that index of 1, drop that new item with that string in there at the index of 1, and when we do, this index is incorrect. We have to reindex this, and this, and this, all the way down. Since we have to reindex all of this, this is O of n. Now you might say, hey, we're putting that in the middle. Wouldn't that be O of 1/2 n? Well, there's two problems with that logic. First is that big O always measures worst case, not average case. The other problem is this. Even if this was a 1/2 n operation, 1/2 is a constant. And we drop constants. So either way, this is O of n. So likewise, when we go to remove this item, we're going to have to reindex everything all the way down. So it doesn't matter if you're adding or removing somewhere in the middle of the array, that's going to be O of n. Now let's look at finding an item. Let's say we're going to find the number 7 in this array. To do that, we'd have to start at the beginning and say, is that 7? No. No. And then we finally get to 7 and it's yes. That means that if you search by value, this is O of n. But if you search by index and you say, tell me what's at the index of 3, those indexes allow you to go directly to that place in memory as an O of 1 operation. This is one of the big advantages of arrays, is that we can find something in an array with 1 million items in it and go to item 400,000, say, and it is an O of 1. But those indexes are also a disadvantage for the arrays if you're adding something to the beginning, as we just saw, because you're going to have to reindex everything. So the big thing that you have to look at when you're looking at a data structure is, what are you using this for? If you need to access things by index, arrays are a great data structure. But if you're going to be adding and removing a lot of items from the beginning, maybe not the best data structure for you, and maybe you should look at a different data structure if that is your use case. But either way, you're making your decision based on big O. So I just want to wrap up our section on big O by looking at how these time complexities compare to one another. So I'm going to bring up the graph, and let's say n is equal to 100. If n is equal to 100, what are all of these going to be equal to? Well, O of 1 is always going to be equal to 1. O of log n is going to be approximately 7 if n is 100. Obviously, n is going to be equal to 100, and O of n squared is going to be equal to 10,000. So you can already see a big disparity between these numbers. But let's say we increase n to 1,000. O of 1 is still going to be 1. O of log n is going to be approximately 10. So 2 to the 10th power is 1,024, which is close to 1,000. So O of log n of 1,000 is going to be approximately 10. O of n is going to be 1,000, but O of n squared is 1,000,000. So you can see that one is going to grow very, very fast. So there are different words and phrases that you'll hear used with each of these. So O of n squared is going to be a loop within a loop. O of n, you'll hear the word proportional. O of log n, you'll hear the phrase divide and conquer. And with O of 1, you'll hear the phrase constant time. So these are our big four that we're going to look at in this course. So now I'm going to take us over to a website that I think is a great resource for learning Big O. It is bigocheatsheet.com. So at the top of the page, you have this graph. These two we're not going to see in this course. In fact, O of n factorial is really something that can only happen if you're writing bad code on purpose. So unlikely that you're going to see that. But you can see that O of n squared is in the horrible category. Remember, O of n times log n is going to be when we are using certain sorting algorithms. And down here is where we want to stay most of the time. So let's scroll down a little bit here. It has these tables. So these are common data structures. So we have time complexity here, and it's broken into average. Notice these are all beginning with the Greek letter theta, and worst, which begins with the Greek letter omicron or O for big O. And space complexity over here, notice they're all the same, except for one of them, which we're not going to build in this course. But everything is O of n, except for that one. So everything that we're going to build for data structures have identical space complexities. And this is one of the reasons why we're going to spend more time on time complexity than space complexity, because for data structures, it's all going to be the same. But it's different when we scroll down to the sorting algorithms. This one for the time complexity, we have best, which is omega, average, theta, worst, O. But see, the space complexities are all over the place. So you have something like selection sort that has a terrible time complexity, but a great space complexity, versus merge sort, which has a great time complexity and not nearly as good of a space complexity. So these time complexities down here only work if you're sorting numbers. If you are going to sort strings or different kinds of data other than numbers, the best time complexity you can get for a sorting algorithm is O of n times log n. I will also include a link to this site. This is a great resource, and I encourage you to go check this out. And with that, that wraps up our section on Big O.